everyone, and welcome back to the Deep Dive. We're diving into the world of unsupervised feature learning today, and get this, the model we're looking at is inspired by, you know, how real neurons learn, like in our brains.
Yeah.
Yeah, the source material for this deep dive is a research paper all about this new approach. They call it the neuron learning machine, or NLM for short.
What's really interesting to me about this research is how they took this neuroscience idea, the Hebbian Learning rule,
Yeah.
and turned it into an actual math model for machine learning.
The Hebbian Learning rule. I feel like I've heard of that before, but to be honest, I could definitely use a little refresher.
Yeah, it's a pretty simple idea, actually,
Yeah.
but powerful, too. It goes back to Donald Hebb's work
Yeah.
back in 1949. He basically said the connections between neurons, they get stronger when they're activated at the same time. You know that saying, neurons that fire together, wire together. That's basically what he was talking about.
Mhm.
The cool thing is, this NLM model, it uses that very same idea.
So how does that actually work? Like, are there physical connections being made in a computer or something?
Not quite. It's more like they created this mathematical model to kind of mimic a neural network, and they focus on how the model encodes information. It's about representing those connections that are getting stronger, but in a mathematical way. It's all about making sure the encoded information really reflects the data it started with.
Got it. So it's like they're not building an actual brain, but using math to capture how those neurons learn. Okay, I'm with you so far, but how do we know the NLM is actually learning something useful? Like, how do we make sure it's not just picking up on random patterns?
Right, that's a good question. That's where this idea of good representation comes in. You can think of it like compressing a file. You want to shrink it down, but without losing any important information. That's kind of like what the NLM is doing. It's called information retention. But it also needs to filter out stuff that's not important, kind of like getting rid of noise. So you focus on what's really important in the data.
So it's about finding the signal in all the noise. How does the NLM do both those things at the same time?
Well, it handles the information retention part by, maximizing the correlation between the input data and its representation after it's encoded. The researchers actually showed this visually in their paper. They looked at how the model got better over time at scent.
Yeah.
Really capturing the important parts of the input data.
So they could actually see it getting better at remembering the important stuff. That's pretty neat. But what about filtering out all the noise? How does it do that?
It has this built-in mechanism that forces it to focus on the most important parts of the input and ignore things that don't really matter. Imagine you're trying to recognize a chair. You can still tell it's a chair, even if the lighting is different, or if you're looking at it from a different angle. That's kind of what the NLM is trying to do.
That's a good analogy. So the model learns what's important about a chair, no matter the small details. Are there any other machine learning things that are similar to this approach?
Actually, yeah. It's kind of similar to a really powerful idea in AI called energy-based models.
Energy-based models. Tell me more about that.
Okay, so imagine it like this. The NLM tries to minimize the energy of the real data it's looking at. And at the same time, it makes random data have higher energy. This way, it's more likely to focus on the real data. Because in this framework, the real data is more attractive. It's a simplification, but it gets the idea across.
So it learns to tell real data apart from random noise by making the real data more attractive.
That's really clever. So I'm dying to know, how well does this NLM actually perform?
Well, let's dive into those experimental results. The researchers did a bunch of experiments to see how this model works in practice. One thing they tested was image classification, which is a pretty standard test in machine learning. They use a data set called MA-NAEST, which is basically a ton of handwritten digits. And what they found was...
Hold on a second. It sounds like we're about to get to the really good stuff. Let's pick up right here in part 2 of our deep dive. See you soon.
Welcome back to our deep dive on the neuron learning machine. So before the break, we were just about to get into those experimental results to see how well this model actually performs. Yeah, you were telling us about how they tested it with image classification using that MNS data set.
Right, so they tested it on MNIST, and the results were actually really impressive. The NLM outperformed other popular models, like autoencoders and restricted Boltzmann machines, especially when they limited the number of hidden units in the model.
So it's not just learning, it's learning efficiently. That's really interesting. What makes that so significant?
Well, if you think about it,
Yeah.
if a model can do well with fewer resources, it means it could be more accessible. We could scale it up more easily, which is really important because we're dealing with bigger and more complex data sets all the time in AI.
That makes sense. So the NLM could be a way to build AR systems that are more efficient.
Yeah.
and don't need as much computing power. What other experiments did they do?
They also looked at how sensitive the NLM is to changes in this thing called a control parameter. It basically fine-tunes how the model learns. And it turned out that the NLM wasn't super sensitive to those adjustments, which is a good thing.
Why is that a good thing?
It means the model is more robust and easier to use. You don't have to spend forever fine-tuning it to get good results. Kind of like having a car that runs well even on rough terrain.
Okay, I see how that would be a plus for researchers.
Yeah, definitely.
Yeah.
Oh, and they also tried something else interesting. They experimented with stacking multiple NLMs together.
Stacking them, like one on top of the other.
Exactly. It's a technique used in deep learning to make these more complex networks.
So instead of just one NLM, they're connecting several together into a kind of multi-layered system.
Right, and what they found was that this stacked NLM did even better than stacked versions of other models, like autoencoders or RBMs.
Yeah.
Again, on that MES data set.
Wow, so this model is pretty adaptable, can handle different setups and still get impressive results.
Yeah, it's really flexible. And they even went a step further. They developed a convolutional version of the NLM called the CNLM, specifically for handling 2D data like images.
Well, that makes sense. Images are everywhere these days.
Exactly. Images are a huge part of the data we use in AI. So having a model that can learn from them is super important. They tested the CNLM on MNIST and also on a more complex image data set called CFAR10, and it showed a lot of promise on both.
It seems like they really put this model to the test, and it passed with flying colors every time. It's amazing how a model inspired by the brain can do so well with these complex tasks.
It really is. And this is just the beginning. There's so much more we can explore with this kind of approach to AI.
It makes you wonder where it could all lead. If we can build machines that learn like our brains do, what does that mean for the future of AI?
That's the big question, isn't it? Researchers and philosophers are really wrestling with this right now. The NLM is a good example of a bigger trend in AI, this move towards unsupervised learning, where machines have more freedom to learn on their own without us giving them specific instructions.
So instead of programming machines with rules, we're giving them the tools to learn and find patterns themselves. Kind of like how humans learn through exploration and experience.
Exactly. And that raises some really deep questions about what it means to be intelligent.
It's both exciting and a little bit daunting.
I agree. It's a big shift in how we think about AI. But before we go too far down that road, I do want to emphasize that the NLM is still pretty new. There's a lot more research to be done to really understand what it can do and what its limitations are.
So this is more like a stepping stone to even bigger discoveries in the future.
Exactly. But even now, the NLM shows us how powerful it can be to take inspiration from nature when we design AI. The human brain is an incredible learning machine, and by studying how it works, we can learn how to build more powerful and efficient AI systems.
It's like nature has given us a blueprint for intelligent systems. We just need to figure out how to read it.
That's a great way to put it. And another takeaway here is the importance of collaboration. The NLM wouldn't exist without computer scientists and neuroscientists working together.
It shows how important it is to bring different fields together to make these kinds of breakthroughs. So what's next for the neuron learning machine? What are the big questions that researchers are focusing on now?
Well, one of the biggest challenges is scaling up the NLM so it can handle much larger data sets. The experiments they did used relatively small data sets. But in the real world, AI often has to deal with massive amounts of data.
So it's like we've built a powerful engine, but now we need a bigger car to put it in.
Exactly. Another area of research is creating more sophisticated versions of the NLM that can capture more of the nuances of how the brain learns. The current model is a simplification. And by making it more realistic, we might be able to create AI systems that are even more powerful and adaptable.
It's incredible to think that we're still just scratching the surface of understanding how the brain works.
We are. And that's what makes this research so exciting. The neuron learning machine gives us a glimpse of what's possible. But it also raises some really important questions about the role of AI in society and what it means to be human in a world where machines can learn like we do.
Those are some big questions, and I think they're perfect for the final part of our deep dive. We'll be back soon to explore those broader implications of the neuron learning machine. Stay tuned. Welcome back to the deep dive. So we spent the last two parts really digging into this neuron learning machine, this model that learns, kind of like how our brains do. In this final part, I thought we could maybe shift gears a little and think about some of the bigger questions that this research raises about artificial intelligence, humanity, and where we're headed.
Yeah, I think that's a great idea. When we think about the bigger picture, the neuron learning machine, and unsupervised learning in general, they make us ask some really fundamental questions like, what does it even mean for a machine to be intelligent?
It's a good question.
In the past, we've always programmed AI to follow rules, specific instructions. But now with unsupervised learning, like with the NLM, we're giving machines the ability to kind of learn on their own. They can discover patterns and make their own conclusions without us telling them exactly what to do.
It's like we're moving from programmed intelligence to something more like, I don't know, emergent intelligence. That's a pretty big shift. And it definitely brings up some interesting questions. Like, if a machine can learn like a human, does that mean it understands things? Is it conscious? Can it be creative?
These are questions that philosophers have been asking for ages.
Yeah.
But now, with AI getting so much more advanced, these questions are more relevant than ever. For so long, we thought human intelligence was unique, something that set us apart from animals.
Yeah.
And of course, machines. But what happens to that idea if machines can learn and think like we do?
It's a bit of a mind bender.
It is.
But I also think it's a really cool opportunity to learn more about ourselves. Maybe by studying how machines learn, we can gain new insights into our own brains.
Absolutely.
Yeah.
Developing AI shouldn't be seen as a threat. It's more like a new tool, a way to learn about ourselves.
It's like we're holding up a mirror to our own minds.
Exactly.
So you mentioned that this kind of research could help us create more efficient AI and understand our own brains better. Are there other potential benefits to teaching machines to learn like humans?
Oh, definitely. Imagine AI systems that can pick up new skills super quickly, much faster than they can now, and with way less data. This could revolutionize fields like healthcare. AI could help doctors analyze medical images, diagnose diseases earlier, and even personalize treatments.
That would be incredible. What about other areas like robotics or self-driving cars?
Yeah, in robotics.
Yeah.
We could have robots that can adapt to new situations and tasks much more easily, that would make them more versatile and helpful. And for self-driving cars, imagine them learning from every mile they drive, constantly getting safer and better.
It's like we're talking about a future where AI isn't just programmed, it's actually learning and growing, almost like a living organism. It's both exciting and a little bit, I don't know, scary.
I understand what you mean. It definitely raises some important questions about the role of AI in our lives.
It does. Like, what will the relationship between humans and AI look like in the future? Will we be partners? Will AI help us solve problems and create new things? Or will we end up competing with each other?
Those are the big questions.
Yeah.
And the answers really depend on the choices we make.
Yeah.
The values we prioritize, how we guide AI research. All of that will shape our future. We have to be thoughtful about how we develop AI and make sure it benefits everyone.
So it's not just about the technology itself, it's about how we use it.
Exactly.
It seems like we need to be having these conversations now before AI gets so advanced that it's out of our control.
I completely agree. We need to be proactive and establish ethical guidelines for AI development. We have to make sure AI is used for good, that helps everyone, and doesn't make existing inequalities worse.
It feels like this goes way beyond just building better machines. We're talking about how AI will impact our lives, our jobs, our privacy, even our sense of purpose.
You're right. This is about understanding what it means to be human in a world that's increasingly shaped by AI. It's complicated. But by talking about these issues and getting different perspectives, we can navigate this new landscape with more care and wisdom.
This deep dive into the neuron learning machine has been quite the journey. We started by looking at the technical details, but we ended up talking about some really big ideas about what it means to be intelligent, the future of AI, and the role of humanity in all of this. The biggest takeaway for me is that the future of AI isn't set in stone. It's something we're creating right now.
I think that's a really important point. The neuron learning machine shows us what's possible with AI, but it also reminds us of the responsibility we have to guide its development in a positive direction.
And on that note, I think it's time to wrap up this episode of The Deep Dive. We hope you've enjoyed exploring this fascinating world with us. And if you're interested in learning more, you can find links to the research paper in the show notes.
Thanks for listening, and until next time, keep exploring.